Today we're going to be looking at unsupervised clustering as a whole, right? And we're going to start by doing theory on some unsupervised clustering algorithms, and then we're going to do a very, very brief example, and then hopefully we can get started on our week 2 project. So, what's unsupervised clustering? So unsupervised clustering is it's like a machine learning technique that groups similar unlabeled data points together, right? And it does this by learning the inherent structure of your data points, right? And let me give you a real application of unsupervised clustering. How does Facebook know to send Priska advertisements on jackets and glasses and hair dye, and it knows to send Mercy advertisements on baby diapers? I like rings and like t-shirts, right? It does that by unsupervised clustering. Priska is similar to the demographic or showcases, exhibits similar characteristics as a person who would like hair dye, glasses, and jackets. And Mercy, being a mom, of course, my timeline and the type of content I consume online would be aligned with the demographic that is interested in diapers, rings, and t-shirts. And it does that without labeling Priska as a jacket girl and without labeling me as a mom. It just looks at what are what are the similarities of Priska and people like Priska and what do they like, and what are the similarity of Mercy and people like Mercy and what they like. So when we do customer segmentation, that is the one place that unsupervised clustering is absolutely a banger. How does Equity know the kind of loans to suggest for you? How does Safaricom know? I don't know if you know Safaricom sometimes sends you offers. How does it know precisely the offer to send you in order to know, in order to increase the likelihood that you're going to click on that offer and actually buy a bundle? All that is unsupervised clustering. We also have unsupervised clustering. Before we had more recommender systems, unsupervised clustering was the baseline algorithm that what's the word I'm looking for? That used to fuel recommender systems. How does Spotify know the kind of playlists to give you? It looks at the songs you listen to, and it looks at other people who listen to other songs, to listens to the similar songs you listen to, and then recommends a song maybe you haven't listened to. All that is unsupervised clustering. It's all about grouping similar data points together by learning the inherent structure and pattern underlying the data. And it's used for tasks like market segmentation, anomaly detection, and data compression. Data compression is more if you go into the instrumentation side, but as a data scientist, market segmentation and anomaly detection is something you're absolutely going to be working with. Now, there are several unsupervised clustering algorithms, right? We are not going to cover all of them, but what we're going to cover will give you the foundations to understand those ones, right? So we're going to cover the foundational algorithms, and then whatever is left is variants of what we are covering today. And I encourage you to go through scikit-learn documentation. It has all those different clustering algorithms. All right. So today we're going to cover a couple. We're going to cover k-means clustering. We're going to cover Gaussian mixture models. We're going to cover kernel density estimation, and we're going to cover a very, very powerful type of clustering algorithm called DB-scan. All right, so let's start with k-means. K-means is hands down the easiest, most intuitive, super easy clustering algorithm to understand. And it's very simple. K-means algorithm just tries to group data points into hard categories. Keyword here is hard categories. Let's go through the intuition one by one. So as you can see here on my screen, we have three clusters. We have a couple of data points and grouped into three clusters. We have the green group, the blue group, and the orange group. Now, what k-means will do, the first thing k-means will do, it will randomly initialize a center. Let me put it this way. It will randomly initialize centers, right? So K means this parameter, or rather hyperparameter K, refers to the number of clusters that you want your algorithm to categorize your data in. And it is set by you. You as the data scientist, you can say, I want K is equals to 2. You can say K is equals to 3, you can say K is equals to 4, K is equals to 10, whatever. But there are ways we can optimize for the value of K. So the first thing K means is going to do, it's going to randomly initialize K number of cluster centers, right? So let's give an example here. So this is 1, this is 2. So we have three cluster centers here. So let's say it says the first center is here, the second center is around here, and the third center is somewhere there. Then it's going to calculate the Euclidean distance. I don't know, Priska, if you want to remind us what Euclidean distance means.
Is it like the
Shortest straight line between 2 points.
Yeah.
Yes, that's the Euclidean distance. So it calculates the Euclidean distance between each data point and the center. So it's going to calculate the Euclidean distance of this data point and the center, the Euclidean distance of this data point and the center it will go and do that over and over again for all of them. Right? Let me just write. That always scares me. Right? So it's going to calculate what's the distance between this point and the center, this point and the center, then this point and this center, this point and this center. You get my drift, right? It calculates the distance between each point and each center. I think I know where they are. Right? So it will calculate the distance between each point and each cluster center. Then based on these distances, right? Based on these distances, it will assign each point to a cluster. So the shorter the distance between a data point and a cluster center, it will say that cluster is this point belong to this cluster. So let's say an example. Right, let me try. Can I define? So the distance, this point, let's say this point, so this point and this point look to be very close. So we can say like this will belong to that cluster. And then this will belong to that cluster. And then maybe this will belong to that cluster, right? So that was the randomly initialized cluster. Then it will update the cluster center with the mean of the points. So in this cluster 1, right, this first cluster, right, this first cluster here, right, if I was to calculate the new center of this cluster, it would mean this point of mine here probably moves somewhere there. That appears to be the next cluster, right? The center of the cluster. If I was to update the center of this cluster, I would say my cluster center moves somewhere there, correct? And if I was to update the cluster center of the orange cluster, I would say my center moves somewhere there, right? Then it goes through that process again. It goes through the process of calculating the Euclidean distance between each point and a cluster center, right? And if you were to calculate the Euclidean distance, it would mean our new cluster. So you update the cluster center with the mean, then you repeat step 3, which is to assign the clusters. So based on our new mean, right, let's look at our green cluster. It would mean this becomes a cluster on its own. And then this becomes a cluster on its own again. And then this becomes, right? This becomes a cluster of its own, and then this becomes a cluster of its own again. Then it does the same thing. Calculates, now it adjusts the cluster center to based on the mean of the data points, right? That's why it's called k-means. So it's going to move this, if we recalculate the cluster center, it's going to move this center somewhere there, it's going to move this center somewhere there, it's going to move this center somewhere there. And eventually, right, eventually it moves the cluster center, does the whole reassigning of the data points over and over again until one, you reach a point of convergence. Convergence can either be reached in 2 scenarios. If you set that the machine learning algorithm should run for 100 iterations, it will stop it will stop updating the centers of the clusters after 100 iterations. Or another point of convergence, you let it run, and the point of convergence is the point at which the cluster centers stop changing, right? So it will update the cluster center, assign the data points to a cluster, calculate the mean. Do that process again, calculate the distances, assign the data points, update the center, and do it over and over again until the point of convergence, which is the point at which the cluster centers stop changing, or whatever iteration that you have, whatever limit you set as the data scientist, okay? Now, k-means is great. It's fantastic.
Is it almost similar with the Kenyan private? Okay, is a slight
Yeah, but it's Nearest neighbors is a classification. This one is a clustering, right? But I mean, I think it could be confusing because they use the same parameter. They both use KK, right? So k-means is great. K-means is great because it's very easy to interpret your results. It's great because it's very intuitive. It's very simple to understand what it's doing, right? But it has quite a number of limitations. The first one, it's very sensitive to outliers. So for example, if we had a data point that's all the way here, it would mean it's going to shift the center of your cluster away. So that would lead to misclassifications because that data point is all the way there. And it also suffers from inaccurate convergence. And this inaccurate convergence is because of one thing. It's because of the random initialization of centers. And let me explain this. Remember, in gradient descent, so this is how k-means also kind of works, right? So remember, it is randomly selecting. It randomly initializes the centers. The center can be anywhere, right? The center can be anywhere. So if it means the center is anywhere, and k-means uses gradient descent as its optimization algorithm, it would mean that if my algorithm maybe randomly initializes that my center is here, as you can see, right? And remember, gradient descent, the whole point is to find the global minimum, but it depends on where you start from, right? So if I start from here, gradient descent will follow the correct procedure, but I will end up in a local minimum instead of a global minimum. And that's usually the issue of when there's a random initialization in your machine learning algorithm. It can randomly start somewhere that leads you to a local minima, and it completely misses the global minima because it will go what's it called? It will go let me see it. Gradient descent will go down. Let me just print a couple of this to explain my point. So gradient descent will go down, 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 down. And when it starts going up, right, it will signal to gradient descent that apana, the slope has changed upwards, and therefore our global minima must be down here. So gradient descent doesn't know the difference between local minima and global minima, and it's because when you start from a random place, that random place can lead you to a local minima, and K means clustering suffers from that. So you can think that you can think that you have reached the point of convergence in your model, but you've actually reached the local minima and not the global minimum. And then it's also very difficult to determine the value of K, especially if you do not have domain knowledge. Now, if you have domain knowledge and you're trying to cluster between income, right? Maybe you're trying to cluster income brackets, and maybe you have worked in the World Bank and you know from your experience, income usually, income brackets are usually like in 4 categories, right? It would be very easy for you to set the value of K. But when you do not have domain knowledge, it's very difficult to set the value of K. And remember, the value of K is the one that determines how many clusters. And maybe in your data there are actually 2 categories of people, but you're forcing this algorithm to classify into 3. There are ways to optimize the value of K and find a better value of K, but it can be tricky. It's easier for you use K means if you have domain knowledge, because it kind of it just makes it optimizes the value of K much faster when you have like contextual data about your industry. And then K-means is not so good with clustered data sets. And I'm going to introduce to you a data set that we call nested clusters. K-means does not do very well with nested data. It does well with data that has that spherical kind of shape, where the clusters are spherical, or they clamp together in a way. But if the clusters are nested within each other, K-means is going to throw off your algorithm completely. K-means is also very computationally expensive and slow. So use K-means when you have a very small data set, or when you want you kind of use K-means as an exploratory data analysis, but in the context of unsupervised clustering. And the reason why it's complex, it's very expensive and very slow, is that for every step, what is it doing? It's calculating the distance between a center and each and every data point, and then updating the cluster center. And then it does that again for each. So imagine you have 10,000 data points, it's doing that computation 10,000 times whatever number of iteration that you've put. It's a very expensive. And when you do K-means for very large data sets, you'll feel it, your computer will absolutely feel it, all right? Now, before I introduce the next unsupervised clustering method, there's one thing K-means does, and it's something that is not aligned with real life. And I'll give an example of this. So imagine you're trying to cluster mid-level employees, junior employees, and senior employees. And you have something like salary and age. So a junior employee is young and the salary is low. A senior employee is probably older and their salary is higher, right? But what about mid-career employees? Right? What about mid-career employees? Mid-career employees are somewhere in between. And you can think of that and extrapolate that into real-world data. Real-world data doesn't have hard assignments. If I was to classify Priska and Marcy based on their preferences, Priska probably likes t-shirts and Marcy probably likes jackets. But a K-means clustering of algorithm is going to hard code Priska and Mercy, it does what we call hard assignments. But real world data kind of exists on a continuum, right? You like, you don't necessarily, I like drama. If I'm looking at television programs, I like reality TV. Doesn't mean I don't like watching the news. So K-means clustering is going to separate you completely. So K-means clustering does what we call hard assignments. But real world data doesn't behave in that manner. Real world data doesn't behave in hard assignments. So Gaussian mixture models, it comes in to solve that limitation of K-means clustering, of doing hard assignments, and instead it does soft assignments. So let's go through how it does soft assignments. All right. Now, Gaussian mixture models is what we call a probabilistic model, right? And it makes one key assumption. It assumes that your data points are generated from a mixture of several Gaussian distributions, all right? And the core work that a Gaussian mixture model is doing, it's trying to find these Gaussian distributions that has generated the data. All right. So unlike k-means, which does hard clustering, right, where it assigns each point to a single cluster, Gaussian mixture model, it performs what we call soft clustering, and it assigns each point a probability of belonging to multiple clusters. All right. And I'll go through it step by step. Now, Gaussian mixture models. Keyword there is Gaussian. Gaussian mixture model, the key assumption that drives this clustering algorithm is that data is generated from Gaussian components. Gaussian is just a fancy word for normal distribution, right? Normal distribution is one of your data distributions, right? A normal distribution looks like so, as you can see there. Now let's understand. So a Gaussian mixture model, the assumption is that your data points, right? These data points, these unlabeled data points that you're trying to cluster is actually generated from a Gaussian component. Let me start by giving you a background in statistics, what a data distribution is. Data distribution is, we also call data distribution probability distributions. You can think of a probability distribution as saying, what is the likelihood, right? What is the likelihood that you are going to observe this data point? And let me just take you back to statistics just a little bit, all right? So that it kind of makes sense about how this underlying assumption actually came to pass. So let's use the simplest probability distribution, which is normal. And this is probability of height. Your x-axis is height, right? And in the middle here, we have people who have a height of, I think majority of Kenyans are around 150 to like 166. So that's like 4 feet something, because I'm 163 and I'm 5'5". So somewhere there, majority of Kenyans are around that range, right? 150 centimeters to 166. And then there's these guys who are like 6'9", right? I don't know how many 6'9" are in centimeters. And there's these guys who are pretty short. What do they call them? They're not called dwarfs. What's the medical term?
I just did want to say that.
Yeah, what's the politically correct term?
Uh,
Midgets. That's
yeah,
even worse. That's much worse. All right. So, and there are these guys who are really short. Let's put them at like 80 centimeters. These are like almost toddler height, right? So, a probability distribution. What I want you to understand what a probability distribution is. This is how you interpret a probability distribution. It says, so this is your probability, right? Your probability curve. So it says, what is the probability of you observing someone with a height of 100 centimeters? The probability is high, correct? What's the probability of you observing someone with 160 centimeters? Very high. What's the probability of you observing somebody with 75 centimeters? Very small. What is the likelihood of observing somebody who is 6'9" in height? Also very small. So anytime you're doing your KDE plot, that is what you're doing, ladies and gentlemen. You are plotting a probability distribution, right? And a probability distribution, if I was to put it in English, is what is the probability of observing a specific value. So you have different probabilities. This is called a Gaussian probability. You have the Poisson, you have the uniform distribution, etc. You have the bimodal, you have the binomial, and that's what they're all kind of communicating. What is the probability of observing this specific value? Now, a Gaussian mixture model, it makes the assumption of, the underlying assumption is that the data we are working with has been generated from many distributions. So the data that we are working with has been generated by a mixture of Gaussian models. And the whole point of a Gaussian mixture model is to find the parameters of this Gaussian distribution component. What are these parameters that we are talking about? Now, a Gaussian or a normal distribution has two main components. First is the mean. The mean is just the center of your Gaussian, right? So as you can see here, my Gaussian component in blue, the center is 0. My Gaussian in red, the center is, Triska?
4.
Yes. My Gaussian in black, my center is, there you go. So mean is the center of your Gaussian component. And then we have variance. What did we say variance is a measure of? Spread?
The spread.
Exactly. So variance is a measure of spread. You can think of spread as the width. So our Gaussian in blue, the width is 1. Our Gaussian in blue, the width is 3. Our Gaussian in black, our width is 2. So the Gaussian mixture model, it assumes that our data has been generated by several Gaussian components, and it is trying to find the mean and the variance of these Gaussian components. Because if I have the mean and I have the variance, I can plot any Gaussian. Provided I have the mean and the variance, I can plot any Gaussian, right? It finds the probability that a data point belongs to a given cluster. So instead of doing hard assignments of saying this point belongs to cluster A, because the distance between point this and cluster A is short, it definitely belongs to cluster A. Gaussian mixture model flips that and says that I'm trying to find the probability that this point belongs to cluster A. So there's a probability that it belongs to cluster A, there's a probability it belongs to cluster B, and there's a probability it belongs to cluster C, A, B, and all that, depending on whatever value you set for the number of clusters, right? So the main assumption made by Gaussian mixture models is that data is generated or can be explained from a mixture of different Gaussian distributions. So Gaussian mixture model tries to find the mixture of Gaussian components that best fit the data. Mixture is just combination, right? So since we are dealing with multidimensional data, our parameters, which is the mean and the variance, they become the mean vector and covariance. What did we say is covariance? I explained this when we did principal component analysis.
Okay. So the way variance is like spread, so variance is that if there are multiple of them.
So variance is spread, and then covariance is multidimensional, and it's about how these data points together are spread or how they are moving together. You know? Good. So that's pretty much Gaussian mixture. That's the theory behind it. So let's take an example of let's do like a geometric intuition of what it's doing, right? So the first thing Gaussian mixture model is going to do, it's going to randomly assign Gaussian components, right? And how it does that, it just guesses the mean and the covariance. Si tumesema a Gaussian component in essence is what? It's the mean and the variance. So tumesema provided uko na mean na variance, you can plot a Gaussian component. So the model is going to start by guessing the mean and the variance of a couple of Gaussian components. All right? Right? So because we're talking about multidimensional, it's going to randomly initialize the values for the mean and covariance, right? And the what we call a mixing weight. And I'll explain the mixing weight in a couple, all right? So then you calculate, it does a step called the expectation step. So for every single data point, it calculates the probability that it belongs to that Gaussian cluster, right? So it's like asking, given where the cluster centers currently are, how strongly does this point belong to cluster 1, 2, and 3? So let me show you. So it assigns responsibilities to each Gaussian component. So in our example here, we have randomly initialized 2 Gaussian components. Sawa sawa? We've randomly initialized 2 Gaussian components. We have 3 points that we want to cluster. So my first Gaussian component, let me see.
So if we randomly come up with like 2 Gaussian points, that means each one of them has a mean and variance.
Yes.
Okay.
Right. So the first one, so let me plot my first Gaussian component and my second Gaussian component. All right, so I have 2 Gaussian components, Gaussian component 1, Gaussian component 2. So I have 3 data points and I have to assign the responsibility. Remember, the underlying assumption here is that your data has been generated or can be explained using Gaussian components. Now, it is generated using a combination of Gaussian components. So the second step is you assign responsibility of generation to each Gaussian component. And this is what it looks like in geometrically. So I have data point 1, right? Here's my data point x1. What is the probability? How much responsibility should I assign to Gaussian component G2? It would be like that, right? And how much responsibility should I assign to G1? So the probability that Gaussian component 1 generated point x1 is low, correct? And the probability that Gaussian component 2 generated x1 is high, right? So let's say you're going to write something like you're going to write something like x1 ama tuseme g1. So G1 is more of a probability. So the probability, it's never really zero. So let's put it like a very small figure. 001 x1 plus, let's say 3 x1. Do you get what I mean? Right? The probability that Gaussian component 1 is responsible for generating point x1 is low, right? So the responsibility of generating x1 is very low for Gaussian component 1. Ask questions, Priska. I am here, right? Right? You're getting. And the responsibility or the probability that x1 was generated by Gaussian component 2 is high. Are you seeing how you're interpreting? It's the same thing we were interpreting here with our normal distribution, right? It's all about probability. But here now, the way we are interpreting this probability is probability of generation. Then we are calling it the response. We are calling it responsibility, right? So you assign the responsibility for each data point. Now, for example, we could argue that a point x1 was generated by Gaussian component 2. Let's look at point x2. What is the probability that Gaussian component 1 generated x2? Should be, yeah, I'm trying to get the center, right? It's pretty high, right? And even if I was to read, as you can see, like it looks like Gaussian component 2 and Gaussian component 1 kind of share responsibility in having generated x2. But when we come to x3, it looks like Gaussian component 3 is the Gaussian component 1 rather is the one that carries the responsibility of generating Gaussian component x3, right? So we could say x1 will be clustered under Gaussian component 2, but x2, which has shared responsibility, how do we make that happen? So you'll end up with something like Gaussian component 1 is 80% responsible, Gaussian component 2 is 15% responsible, Gaussian component 5 is Gaussian component 3 is 5% responsible for generating point 1. And you're going to have that for all the points in your data, right? Now, there's something called the mixing weight. And let me show you once we get before seeing the data. Okay. So after you have assigned the responsibility, there's something called a mixing weight. You can, by the even mixing weight is complicating it. I'm just saying it's mixing weight because that's the vocabulary for it, but think of it as a weight, right? Weight is just each Gaussian component has a weight. That's pretty much it. Each Gaussian component has a weight. So the bigger your Gaussian component, the bigger its weight. You understand? Right? So that's how you end up with assigning responsibilities. After you assign the responsibilities, now you can update the parameters. You can update the mean, you can update the covariance, and you update the weights. And let me try and give an example here. Just give me a sec. I remove all this. So, once, as you can see, let's say our initial Gaussian components looked like this, like the red Gaussian component and the yellow Gaussian component. Remember, you're trying to find the Gaussian components that best fit the data, as you can see, right? So you're going to, as you update the mean, remember, if you update the mean, covariance, and weights, you change the size. You can think of weights as the size of the Gaussian component, and then the mean and variance is now the actual parameters of the Gaussian component, right? So you're going to go to a Gaussian component like looks like this. As you can see, the red Gaussian component doesn't fit the red cluster properly, and then it goes through that cycle. You update the parameters, which is the mean, variance, and weights.
Okay, so when you update the date and then the variance, you just come up with them, like how do you arrive to that? Or how do you arrive now the variance and the mean? And we just how exactly so that you can keep on updating it?
So it's usually a very complicated like formula like here.
Yeah.
But you don't need to understand the formula, just visualize, like understand that's what is happening in the background. It updates the mean and the variance, right? It updates the mean and the variance, and that changes the shape of the Gaussian component. And it will change that shape so much. Let me see. To love this. It will go through that cycle of it randomly initialized Gaussian components, assigned responsibilities, right? Goes through a process of updating those parameters, then does the same thing, assigns responsibilities, then updates the parameters, and then assigns responsibilities until it gets to a point where your parameters are no longer changing significantly. And that's what we call the point of convergence. Can you see? You started with Gaussian components that look like this, and then it kind of fits the data a little bit, and then eventually you find Gaussian components that perfectly fit your clusters. That's pretty much Gaussian mixture models, right? And it allows for soft assigning, right? Yeah. So, and even when you do cluster analysis using Gaussian, it because Priska has not been assigned so hard. Because me, you can assign me mother. I'm older. I have all the check boxes of mother above 30, right? What if you get a child at 12, right? That's if you have a child at 15, probably your social media kind of looks like mine, right? So K-means clustering would say that is a teenager and give her things for wamlambes and whatever you guys do, right? Yet I am her demographic, right? So Gaussian mixture models allows that soft assignments, right? And it does very well for, those data points that are, they're not outliers, but they are a little bit different from the norm. Like the 14-year-old mom, the seven, even for me, when 20 is quite young, the 20-year-old mom, such things, right? Tahasa, any question? So the process of updating the parameters is it's math heavy. But do you understand what is happening in the background? All you need to know is you understand what's happening in the background and when to apply which method over the other.
So regardless of the method that you use in clustering, at the end of the day, we'll have to arrive at a point of convergence by going through this process over and over again.
Yes, but there are evaluation metrics to help you choose one method over the other,
Yeah.
right? Good. So after it does those probability assignments, it updates da 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 da. Remember, okay, I can even tell you by the way, after it does the probability assignments, the mean can be it will just update the mean because the mean is the center of the cluster, right? And also it can calculate the covariance. So the So let's say it says it starts with this, right? With a specific mean for each. whatever is soft assigned and whatever is hard assigned, the soft assigned ones can be multiplied by the level of responsibility. So if this point, like let's take a point that's right in the middle, if this point is 50% here and 50% here, it would like contribute 50% to the new to the new center. You get? Then it will update that center. And you'll keep on updating until the but I can do for you. Would you like to know the math behind it? Fine, fine. Just know it's going through that process. Okay. All right. So the next one, we have kernel density estimation. All right. And kernel density estimation, to be quite honest, is one of the easiest. Let me just show you what it does. The intuition behind it is very nice and clean. All this. All right. So let's say we have the following data points. We have 10, we have 15, we have 25, we have 50. Remember what I showed you about normal distribution. Normal distributions it answers the question, what's the probability of observing this value? So if I have a data set, and in this data set I have observed 10, 15, 25, and 50. If I was to plot a normal distribution on the value 10, the likelihood of me observing 10, it's already observed in my data, right? So the likelihood of me observing 10 should be the highest probability, correct? The likelihood of me observing 10 should be the highest. The likelihood of me observing 15, the highest as well. The likelihood of me observing 25, the highest as well. The likelihood of me observing 50, the highest as well. So what kernel density does, right? Gaussian mixture models tries to find Gaussian components, these big Gaussian components that best fits the entire data. Kernel density estimation takes that to the extreme. And instead of fitting 1, 2, 3 Gaussian components, remember in Gaussian mixture models, you're the one who defines how many Gaussian components you want to fit. In kernel density estimation, it takes Gaussian mixture models to the extreme and fits a Gaussian component to each and every data point. So it's going to come and fit a Gaussian at 10. That's not a good one. It's going to fit it at 10. It's going to fit another one at 15. It's going to fit another one at 25. It's going to fit another one at 50. Now, then kernel density estimation just comes to smooth over, right? So kernel density estimation just comes and takes all these Gaussian mixture models at each data point and just creates an average probability distribution, something that eventually looks like this. So distribution like this, like that, like this, like that, like that. And then that's pretty much but then that's pretty much how KDE that's what KDE is, right? It's not clicking. Let me find an example. Let me find an example. I'm trying to find an analogy.
Okay, if I okay, let me see if I get it. So, uh, first we have to get the probability of getting a 10. It's 5 and 50. So once you have the probability of getting that, of course, we will not we will do a Gaussian plot over the point that you're getting. If it is 10, the probability of getting 10 is
Sorry.
the probability of getting a 10, and then so here the center is
Actually, I'm doing the wrong. Let me explain something. Let me get something. Let's get something straight. KDE is not necessarily a classification algorithm. It's more of a EDA for clustering. So what KDE will help us do, and let me use better examples by the I'm seeing, and now I see where it can be completely confusing. Let me show you. So this becomes like, I can get something here. Let's see. All right. So let's say we have the following data points, right? We have 10, 30, 300, 500. So KDE is going to plot a Gaussian mixture model, a Gaussian distribution rather, on each and every one of these data points. Then KDE comes in to smooth over this different. Now, yes. So KDE helps us with doing something. KDE helps us identify natural clusters. So if I was to, let's say, if I was to remember, KDE does like an average of the probabilities, then it comes up with one probability. Let me show you. So we have this Gaussian for 10, for 30, for 300, and for 500. So if I was to come up with one KDE, it would look something like around 10 in a peak, in a peak, in a peak, and then hapa in a drop, juu hakuna kitu. Ngoja, acha nijaribu. It peaks around here and peaks also at 30, then it drops a little bit, then it peaks around 300, like that. Are you seeing we have combined all the Gaussian, we've combined all the normal distributions, right? Such that if I was to read just this average probability distribution, it would mean the probability of getting maybe a 10 should be high, right? Because it should probably even be higher than a 1, June, right? The probability of getting a 30 is also high. The probability of getting something like, let's say, 100 should be low because 100 was never observed in the original data set. The probability of getting 300 should be high. The probability of getting 500 should be high. Now, what this tells you, what does it tell you? It tells you there are two clusters in your data. And that's how KDE is used as an exploratory data analysis for clustering algorithms. It kind of comes in to validate whatever K, maybe you've gotten with K-means, whatever other method. So you can use KDE. It's not a clustering algorithm per se, but it helps you with naturally identifying some clusters, right? All right. Now, the other clustering algorithm we have is hierarchical clustering. And hierarchical clustering is just as the name suggests, used to cluster data by building a multi-level hierarchy of clusters through either merging smaller clusters or dividing larger dissimilar clusters. Hierarchical clustering is very intuitive. You have two types. We have agglomerative, which is bottom up, or divisive, which is top to bottom. Now, this is how it works. For bottom up, which is agglomerative, each data point is treated as its own cluster. Then you calculate the distance between your clusters. Whichever cluster is closest, merge them. Then update again. Kama nimecluster Priska na mimi tuko pamoja, na Anthony na Bridget wako pamoja, tutacalculate. Now me and Priska become cluster A, Anthony and Bridget become cluster B, Cyril and Jesse become cluster C. Then we calculate the distance between cluster A, B, and C, and then we find that cluster C and B are closest, we merge them together. Maybe as we are closest with cluster D, we merge together, we become a cluster. It does that over and over and over again until the entire data point becomes one big cluster. That is agglomerative, from bottom up. Divisive hierarchical clustering is the opposite. It treats the entire data set as a one cluster first, right? Then it calculates the distance between points. Whoever is the farthest, you split. And then does the same. Calculates the distance. Whoever is the farthest, split. Split, split, split. You split until you get back to each data point being a single cluster. That is all hierarchical clustering is. Now, what is the essence of hierarchical clustering? Just like in KDE, it can help us identify natural clusters, right? And it does that through a visualization called a dendrogram. So what we have here is a dendrogram, right? Now, how do you interpret a dendrogram? You look at these vertical lines. So if I was to look at this dendrogram, I am seeing about about four prominent vertical lines. The longer the vertical line, the wider the separation, or the wider the difference between clusters. All right. So I'm looking at 1, 2, 3, 4. I'm looking at four very prominent clusters, and that tells me now nikienda kufanya k-means clustering, let me use 4 as k. Nikienda kufanya Gaussian mixture models, let me use 4. Unaona, KDE and hierarchical clustering kinda gives you a place to start. Ndio nisianzie ground zero nikiguess what the parameter k should be, or what the parameter, how many Gaussian mixture models I should use. We're going to do this more practically, and you're going to see like how we interpret a dendrogram. Now, I don't know if you want to give it a try. How many clusters do you see in this dendrogram? And it will also highlight another issue with hierarchical clustering. How many do you see? I told you, you look at the vertical lines. Look at the vertical lines. How many vertical lines, how many prominent vertical lines can you see? So 1, 2, 3, 4. Yeah, you could totally argue about four prominent vertical lines. So you can totally start at k is equals to 4, or 4 Gaussian components. Now, another thing in hierarchical clustering is the linkage criteria. Linkage criteria is just how do you calculate the distances in your model. We have single linkage, which is about the nearest neighbor. So the difference, the distance between the nearest person in your cluster. Like, remember, you are either taking apart clusters or you're merging clusters. So how do you, linkage criteria defines how that is done. So single linkage means your nearest neighbor linkage, right? So in this cluster, in cluster RNS, the distance between the nearest neighbor, that is what will be considered, instead of the distance between something else, right? Complete linkage is the distance between your farthest neighbor. Average linkage, it calculates the distances between each data point and each data point, right? And then word linkage is something called intercluster, within cluster variance. Now, I usually like giving this as an assignment to students. On Monday, you will come back and you're going to discuss linkage criteria used in hierarchical clustering. Hiyo inakuanga sasa homework yenu. Sawa? If you are ready, we can go to DB scan, or we can take a 5-minute break and then we go to DB scan. Sawa? T. Yes. Hapo tu ukiingia hapo kwa kona.
Coffee will make me
Pardon?
I'm saying at least some coffee will help me.
Kwani hujaamka Priska? It's 11:30 in the morning. You see, class running algorithms haina mambo mingi. I'm trying to come up with an example here. Why are you always having a cold?
I have sinuses. So yeah.
Oh, wow. Man, allergies. So you can't even, huwezi fanya hata ukulima.
Says it?
Huwezi fanya ukulima.
Nafanya nikiwa nyumbani simfanyia watu nikiwa.
All right, just digest that. I'm trying to come up with a fake data set to explain DB scan. Especially explain to you what a nested cluster is. Okay. Why majority of what we've discussed will not doesn't work for real world data. All right. All right. You ready? Can I grab some tea then? Try to let's switch gears a little bit. Let me explain a little bit of theory and then switch gears. Now, okay, so the next clustering algorithm, and by far the absolute most powerful, right, is what we call DB scan. So DB stands for density based spatial clustering of applications with noise. Despite its long name and its scary abbreviation, its intuition is actually quite genius. Now, DBScan came to be because because of in real world data points don't exist spherically in perfect spheres, or in even Gaussian components can do the crazy complex data underlying structure, but still Gaussian mixture models still suffers from one limitation. It doesn't perform very well for what we call nested clusters. What's a nested cluster? It's a cluster within a cluster. For example, this is a nested cluster. The green cluster is nested within this one. You see that? Now, real world data tends to sometimes look like this. And DBScan comes in to help you with clustering, especially complex nested data sets. And majority of complex data sets tend to have this kind of underlying topology, this nested topology. So DBScan stands for density-based spatial clustering of applications with noise. I still have to read that. And it's a very powerful clustering algorithm, and it groups points that are closely packed together in space. So unlike the other clustering algorithms, it doesn't require you to specify the number of clusters. There's no K, there's no specify for me the number of Gaussian components. It's usually an exploratory tool for clustering algorithms. So you can do your DB scan even before you do your k-means, blah, blah, blah. So the main idea is beautifully simple, okay? DB scan defines a cluster as a dense region of points surrounded by a region of low density. So it's density based. So a cluster, let's see, right? A cluster is a region of high density surrounded by a region of low density. Isn't that technically true? Do you see that? A region of high density surrounded by a region of low density. So DBScan has developed a way to find these regions of high density surrounded by regions of low density. And I'm going to show you an example. Now, let's go step by step. How does DBScan find this? It finds this using three, how do you say this? Three concepts. Yeah, let me explain to you using the three concepts. So concept number one is the concept of a core point. What is a core point? A core point is a point surrounded by a minimum at least n neighbors. This n, let me just change this. I don't like how big it is. There you go. This n is defined by u. So it's like a hyperparameter. And the neighborhood, right? The neighborhood within which these neighbors exist is defined by a parameter we will call epsilon, right? And epsilon is just a radius. And let me explain. Let me just borrow this, right? And put it right here. How can I do a nice radius without killing? So the background is empty. Perfecto, perfecto, perfecto. So I'm just gonna make that. So epsilon, right? Epsilon is simply the radius of your neighborhood. So every point within that radius is a member of that cluster because it's considered a neighbor. So let's say this is my radius, right? And within that radius, what DBScan does, it's going to find the neighbors. Let's say we are starting with this particular point. Let me change this to red. Right? Let's say we are starting with this particular point, and this is my radius. So now we need to put this at the center. Let me make my radius bigger or increase the number of. There you go. So using this epsilon, which is my radius, I'm going to determine my neighborhood. So how DBScan does it, each point becomes the center. Each point becomes the center of your radius. It's now the center of your neighborhood. Basically, think of it as saying, I'm trying to find my neighbors. What is the distance that I'm defining my neighborhood? That distance is determined by a parameter we call epsilon. So it will go to each data point and it will become the center of the data point. Then it will put this radius and say, these guys are my neighbors. So this guy over here, let me color it blue. No, color it blue. This guy over here is my neighbor. This guy over here is my neighbor, right? So this becomes your neighbors. Just give me a sec. Notes. Okay. So a core point, right? The whole point is to determine what is a core point. And a core point is a point that is surrounded by at least a specific number of neighbors. Let's say, for example, my n here is 3. As you can see in this neighborhood, I have 1, 2, 3. So it means this point here becomes a core point. Okay, now we've established that this point is a core point. Let us look at this point. If I make this point, let me color them. Let me change the background and include. If now I'm trying to see if this point is a core point, right? So how many neighbors does it have? It has this core point as my neighbor, it has this point as its neighbor, and it has that point as a neighbor. Therefore, this becomes a core point. Sawa? Now, it does that to each and every data point. Let's just keep moving until we find all the core points. Let us test if this point over here is a core point. It has how many neighbors? 3. It has at least 3 neighbors. Therefore, that makes it a core point. And we keep on moving until we find all core points. Let's make this guy our neighbor. Let's make this guy our center. Is it a core point? Does it have 3 neighbors? So it's not a core point. If it's not a core point, we call it a border point, and we'll give it a different shade. Let's give it, I don't want to give it green. Let's give it, let's give it this, oh, geez. Let's give it this turquoise color. Let's give it, oh, that's too close to our blue. Too close to our red. Or we give it, yeah, let's make it that. Or we give it a purple. Yeah, let's make it a purple. Cool. So that is not a core point. So let's go in the entire data set just finding core points. So we make this our center, right? This becomes a core point because it has 1, 2, 3 neighbors. So we make that a core point, right? And then keep on finding our core points. If I put this in the center, do I have neighbors? 1, 2, it doesn't fit the bill. We make it, kwani imeenda. Make it that. How do I add that? All right, let's keep on finding our core points. If I put this at the center, if I put that at the center, does it become a core point? No, it only has 2, it doesn't have 3 neighbors. So we make this a border point. And let's just assume this becomes a, oh, can it become a core point? If I put it at the center, it will not. So let's just assume we are now defining core points like that. That becomes a core point. If I put this at the center, I think that can become a core point. And then this is a core point, right? This, if I put this becomes the purple one, and so on and so forth. Okay, so the first step is to find all the core points in your data, and all the core points in your data are the points which have at least n neighbors. N is you set. If you want 2 neighbors, 3 neighbors, 4 neighbors, 5 neighbors. Now, after you've set the core points, the next thing to do is you're going to start assuming, okay, now we want to assemble our cluster, right? We want to assemble our cluster. So your cluster is going to be, what's the word I'm looking for? Your cluster is going to be it's going to be your surrounding neighbor. So we're still going to do the epsilon. Let me just remove this. So edge of the cluster. So now we want to start assembling our cluster, right? We've already defined what is a core point and what is what we call a border point. So a core point is the one that is surrounded by at least three neighbors based on this epsilon. So let's start our cluster building from here, right? We will do again our epsilon, right? So how many, wait, how does it assemble the clusters? Let me just get something right. Let me see my notes. A sec. Okay, so we have our core points. So our core points are the ones in red. Okay, our core points are the ones in red. So let's say I am starting my cluster from this particular point. So the first thing DBScan will do will assign it will assign each point and define it either as a core point or a border point, right? Then after it does that assigning, it now starts building the clusters. So let's say my cluster is starting exactly from this point. I will look at which of, let's see, let me start somewhere in the middle, like somewhere there, right? If my cluster is starting from exactly this point, it will look at who are my neighbors in this neighborhood of mine. If you are a core point, you automatically get included in the cluster. So my cluster size joins like, it increases like that. Do you see that? Right? See my notes. Decreases. So any core point automatically increases the size of the cluster. So if you're a core point, you automatically get included in the cluster. Now, the difference between a core point and a border point is it really comes out specifically in the process of defining, or rather in growing the cluster. So for example, we started with this point and we said that is our first cluster. And then we drew our neighborhood. Anyone who's within that neighborhood and is a core point automatically qualifies to be in the cluster. Now, in this cluster, we now have this cluster, because of virtue of these points, will increase the size of the cluster. When it increases the size of the cluster, it includes this border point. Then it increases the size of the cluster again. Anyone who is automatically, any core point automatically qualifies to be in the cluster. Then it improves it, it raises it kidogo, and you get a cluster there. Now, the difference between a core point and a border point is in how it can grow the cluster or not. A border point cannot grow a cluster, but a core point grows the cluster. So, for example, this point here, right? This point here has grown the cluster, and it should actually, if I was to draw a radius, this is actually a core point. The border points are these ones here, right? So it increases the cluster like so, right? And our neighborhood increases right? But when your neighborhood reaches the border point, it can't go beyond that. The border point can be part of the cluster, but it doesn't expand the radius of the cluster. The border point qualifies to become part of the cluster because it is close to a core point. But if the border point doesn't increase the size of the cluster, only the core points do. So eventually you're going to end up slowly by slowly this becomes part of the cluster, and eventually you'll end up with something that mimics that shape, but it's still core points, border points. And that's pretty much how it works. It just assigns who is a core point, who is a border point, and it grows the cluster like that. And the whole essence is, by the time the cluster gets to the border point, which is here, remember, we've said the difference between a core point and a border point is that the border point doesn't increase the size of the cluster. So it kind of confines it because the cluster stops growing. And that's basically DB scan. That's all it does. It's not really a mathematical computation, it's a distance kind of computation. And that distance is based on how dense the data points are. That is pretty much it. And DB scan is usually very popular in anomaly detection because it is going to highlight for you such regions where they are very far away from the clusters. All right? That is pretty much it. The next thing I want us to do, I want us to do a practical. Or I show you an example. All right? So you can find more on DB scan there. All right, here we go. I have an example here of clustering, and we'll go through it quickly, so that, but I'll share the notebook and you can use it as a reference. So this morning I was trying to curate this notebook for this class, and I chose to do a use case for Spotify, right? Like I said, clustering, the business case is usually for market segmentation, customer segmentation, music recommender systems, because the people who listen to Wakadinali most probably listen to Bridget. No, Bridget Blue is R&B. Who's very close to Wakadinali? Who's like a Kenyan rapper? Or let me say, the people who listen to Bensoul highly likely also listen to Sauti Soul or listen to Watendawili. And the people like me who listen to Beyonce, we probably also listen to Rihanna. You get? So we have similarities, and that's how Spotify. The the Spotify doesn't use clustering right now. It uses a more advanced deep learning version of clustering, which we'll do in our week 4. But one of the recommender systems started, this is where they kind of started from. So I have an example here of Spotify. I will absolutely share the data as well as the notebook. And we are just trying to, what's the word I'm looking for? I'm trying to categorize different songs rather, based on music qualities like danceability, violence, energy, if it has explicit words or not, if it has keywords, the liveliness, the loudness, the speechiness, and the tempo, just like technical characteristics of what makes a song from a musical like perspective. I remove my duplicates, I look for missingness, which it didn't have any, and I start doing my simple exploratory data analysis, of course, looking for outliers. The EDA is not extensive, but you get the gist. Of course, I look at if there's any multicollinearity, I scale my data, and then I apply my clustering algorithms. Remember, we said KDE and hierarchical clustering is kind of like you can use it as an EDA before you do your actual clustering, and they help you to identify natural clusters in your data. All right. Now, can you identify any can you identify any clusters in our data here based on the dendrogram? Give it a shot. And there's also a reason why I hate hierarchical clustering because of that. Interpretation of dendrograms can be very tricky. Remember, all hierarchical clustering does, right? It just shows you how your data is related and it builds a tree from that. So, what a dendrogram is that tree that it has built. Okay?
There's so much interconnected
There you go. There you go. That's why dendrograms can be quite tricky, right? They can be very messy. For some data points, for some data sets, they look clean and it's very easy to interpret, and you'll see cluster one, cluster two, cluster three. But for most, yeah. So how you interpret a dendrogram is the higher the vertical line, the more the differences between the two. So straight up, the tallest vertical lines are these first two, this and this.
Yeah.
Yeah, that and that. And clearly, it even does for you the coloring. They are clearly two distinct clusters. But if you wanted to go a little bit deeper, I'd probably argue, let me see, I'd probably argue points are actually connected. Let me see. I'd probably so how you interpret a dendrogram is the tallest vertical lines that do not have a horizontal line going through them. And straight off the bat. So let me give you an example. I was thinking of saying maybe this cluster and this cluster. But you see, they have horizontal lines going through them. But you see, these two vertical lines don't have any horizontal line going through them. Right? And that's the other limitation of hierarchical clustering. Very good. It's an exploratory data analysis step in clustering problems, but they become very difficult to interpret, especially if your data is very interconnected. But just so that you have the code and you know how to interpret a dendrogram, you have it there, right? For hierarchical clustering, I'm using it to give me an idea of a good value of clusters. For my other clustering, I used a library called Spicy. You'll definitely you'll read the notebook. Right. Now I can apply k-means clustering. So for me, I said, okay, let me see, can I identify, for me I can say like one, but this one has a vertical line going through it. Can I say, no, it's still two clusters. From the dendrogram, it's still two clusters. So if I wanted to apply k-means clustering, this is how to do it. So you just create an object, a k-means object. You use the special word k means, and you just define the number of clusters. Even if you do not put any of this and you just put k means and you define the number of clusters, you're good to go. And then you fit it on your scaled data, and there you go. I want to get the labels from my k means, and I want to get the actual centers, and there you go. Cluster labels 333 da 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 da. That's your k-means. And then in k-means, we have how do you, in clustering algorithms, how do you define that one? How do you decide that one algorithm is better than the other? You use a metric which we call the silhouette score, right? So you will be seeing the silhouette score is just the way we say R2, the way we say precision, the way we say recall. Now in classification algorithms, we have what we call a silhouette score. The higher the silhouette score, the better. The lower the silhouette score, the worse. So our k-means clustering, our silhouette score is 0.22, 2225. Now, in k-means, remember you have to optimize for the right value of k. How many clusters should I actually go for? Now, the dendrogram is supposed to give us a place to start. The dendrogram ikikwambia start from 5, you don't start from 2, right? But it's not a given. You still have to optimize for the value of k. And how you optimize for the value of k is literally trial and error, guys. As you can see here, I am fitting a k-means clustering algorithm to a range of k. And my range of k is from 2 to 11. So what I'm saying here, fit a k-means when the k is 2, fit a k-means when the k is 3, 4, 5, 6, 7, all the way to 11. Once I fit my k-means, I'll plot the silhouette score, which we also call inertia. I'll plot the silhouette score against the number of clusters. And this is called the elbow method. Oh, gosh, terrible backache. This is the elbow method. It's the elbow method where we learned in. Where did we learn the elbow method? K nearest neighbors.
Yeah.
And what else?
Okay, I really remember when you were mentioning that.
Yeah, so the elbow method, it's interpreted the same way. So the part of the elbow, that is the best, that is the optimum number of k. Can you interpret it from here? What do you think our optimum number of k is? So you have two options. You can plot the inertia or you can plot the silhouette score. Or you can plot one, right? So k-means inertia you can get from the way you can extract it from the k-means object itself, right? So inertia is another evaluation metric for clustering algorithms. So you can plot either the inertia or the silhouette score. I prefer to plot both so that they can validate each other. Kind of like a way to counter check. Silhouette score imenipatia a optimum k value of this. How about inertia? So Priska, what do you think the optimum value of k is based on the elbow method and how we interpret that?
Like for example, in the silhouette score, I think it should be around 4. Where the elbow is, right?
Where's the elbow?
But we're gonna, what if, okay, where the elbow is and where it's at the low value. Because, for example,
It's the part where there's no significant reduction in either inertia or silhouette score. So it's not necessarily the lowest, it's where there's no significant. Because remember, you're trying to balance, you're trying to be efficient, right? Si lazima ikue at the very lowest, right? Because ukisema it's at the very lowest, those are computational resources. So the elbow method comes in as a way to help you reach a trade-off. So the elbow, even if sometimes the elbow ichorangi vizuri, this is the interpretation of the elbow. It's the point at which any increasement haiko significant. So like for example, in this context, the point at which or the number of k, the value of k at which the inertia or silhouette score doesn't decrease significantly. But whenever the elbow plot is hard to interpret visually, interpret it given its definition of what the essence of the elbow plot was. It was to identify the value of K at which there isn't a significant decrease in either the silhouette score or the inertia score. What do you think that point is? I'm thinking it's around, yeah, around 6, 5 up. Nuggets, yeah, correct. 6, 5. You can, sasa, unaona, the whole point of the elbow method ni kuguide. Sasa wewe uko na option ya either utafit K-means at 6 ama ufit at 5, or even better, fit at 6 and 5 and compare the silhouette scores and take the one that has the lowest silhouette score. All right. All these things are usually to guide you. Right. So for me, I saw that my best is at 5. Juu enyewe nikiangalia difference ya this inertia score na at 5 and 6 mi sioni ikiwa kubwa. Sindio? So I fit my K-means using 5, which was what I had initially done, I think, in the beginning. Yeah, I had fitted it at 5. All right. Okay. And then how to visual the results of the K-means. Okay. And this is where PCA and clustering come together. Now, PCA, I have reduced my data into 2 components. Remember, PCA is not only to help you, be computationally efficient, right? But it's also to help you visualize. And it comes super handy when you're dealing with classification tasks and when you're dealing with clustering. So here I have minimized my data into 2 principal component analysis, which allows me to plot my data in a 2-dimensional screen, like in my VS Code, right? I apply my K-means, but I am applying it on my PCA data, and there you go. Now I've plotted my clusters. I have a red cluster, I have a green cluster, I have a purple cluster, I have a blue cluster, and I have this weird orange cluster that all over the place. That is K-means. So what we're going to do, we're going to see how this visualization changes based on which algorithm we use. So, but the process will be the same. Kama ni K-means optimized for K, then I did my PCA to allow me to visualize my data. And then I applied K-means using the optimal value of K. So then let's do Gaussian mixture model. Same process. You create a Gaussian mixture model object, right? And for Gaussian mixture model, the important hyperparameter becomes how many number of components you need. So if anywhere I am setting the number of components, please always note there is definitely a step for optimizing the number of components that you have gotten. All right. So remember, always use scaled data. There's my Gaussian mixture models. Remember, the silhouette score is how the silhouette score is how I check which model is performing the best, and then you have to optimize for the number of Gaussian mixture models. Now, unlike in K-means where you're using the silhouette score and the inertia score, in Gaussian mixture models we use something called BIC and AIC. Let me just find the definitions for that. BIC and AIC, they stand for something information criteria. Yeah, so AIC stands for archaic information criteria and BIC stands for Bayesian information criteria. They're just used to compare. They just tell you which model is best fit for your data based on model complexity and like how well they're a measure of goodness of fit. Yes, that's the correct one. They're a measure of goodness of fit. So when it comes to Gaussian mixture models, you use AIC and BIC to determine goodness of fit. Remember, Gaussian mixture models ilikuwa inasema nini? Gaussian mixture model ilikuwa inatafuta the Gaussian components that best fit the model. So AIC and BIC give you a metric for determining or for translating goodness of it. Okay. So AIC and BIC, you still use the elbow method. So you're going to plot the number of Gaussian components, right, versus the information criteria, which is AIC and BIC. And the point at which that elbow appears, that is the number of Gaussian components that you should have. And for me, I think I arrived at 3. You see, the difference between 3 and 2 seeming, 3 and 4 rather, seeming. The difference between 4, 5, 6, 7, it's almost insignificant. Actually, this is one of the best elbow plots I've gotten. They can be quite hard to interpret, especially if it doesn't come with a clear elbow. So ukiona elbow funny usistuke. It happens to the best of us. Okay. So here I choose the optimum value of how many Gaussian components I should have is 3. And you can see I significantly improve here where I did a Gaussian components of 5 Gaussian mixture models. I was getting a silhouette score of 0.03. That's a very poor silhouette score. But when I optimize it to 3, at least I get 0.1, a huge improvement. Okay, and now we do the same thing. We'll apply principal component analysis to reduce our data into 2 dimensions to allow us to what's the word I'm looking for? To allow us to visualize. And these are the results of my Gaussian mixture models. Now we do the same with DB scan, the exact same thing, right? And radius of the neighborhood, which is the minimum number of points that define a cluster. Yeah, so the first step in DB scan is choosing the epsilon, which is the radius that defines our neighborhood. And you do that using something called K distance, again, based on the elbow method, right? So the elbow method is approximately here. Tunaona elbow method imeshika mahali hapa. Tunaona, that's why I've come up with 0.3. Okay, elbow method 0.3, and therefore that's the distance I should use. It comes up with 11 clusters. Can you imagine that? 11 clusters, right? So DBScan found 11 clusters on the reduced data. Let's see the silhouette score. The silhouette score is 0.3. Yeah, it has a better silhouette score than K-means clustering. And there you go. Yeah, not the best, but this is how DBScan looks like, and everything else is noise. That's pretty much it. Now, what you usually come now and do is you do cluster analysis. So you, just like you did the credit score modeling, you will pull the clusters, and then for cluster 1, what are the defining characteristics? Cluster 2, what are the defining characteristics? Cluster 3, what are the defining characteristics? And I'll leave that for you guys to do on your own for your week 2 project. Any questions? A lot to digest, I know.
Yeah.
I know.
Yeah, but I think when we go and working on the assignment part, to make ourselves because I'm really
Practical.
Yeah.
Yes. So yeah, I think we can end class there. I don't have anything else to add.